Our universe holds at least 30 worlds that might be someone else's home. We are in the middle of a breathtaking cosmic treasure hunt, searching for exoplanets, planets orbiting distant stars that could support life. By the end of this journey, you will know the names and secrets of these 30 potential havens. We will explore a planet cloaked in a thick, steamy atmosphere and another locked in an eternal gravitational dance. What does it truly take for a world to be called alive? Our journey begins right next door, cosmically speaking. Just 4.2 light-years away, a world named Proxima Centauri b orbits our closest stellar neighbor. This planet holds a profound significance in our search, a rocky world with a mass strikingly similar to Earth's, nestled within what astronomers call the habitable zone. This is the region around a star where temperatures might be just right for liquid water to exist on a planet's surface. But this potential paradise is a world of extreme contrast. Proxima Centauri b orbits a red dwarf star, a type of star far smaller and cooler than our Sun. This close orbit, necessary to stay warm, likely results in a phenomenon known as tidal locking. One side of the planet would be permanently bathed in daylight, while the other is locked in an eternal, frigid night. The border between these two extremes, the terminator line, could be a strange and dramatic landscape. Yet the greatest challenge may come from the star itself. Red dwarfs are notoriously tempestuous, frequently erupting with massive stellar flares. These eruptions of radiation and charged particles could be powerful enough to scour away a planet's atmosphere over billions of years, stripping it bare and exposing any potential life to the harshness of space. So, is Proxima Centauri b a scorched wasteland, or could a thick atmosphere or a global ocean protect a hidden biosphere in its twilight zone? The answer remains one of astronomy's most tantalizing mysteries. Proxima Centauri b's challenges reveal a stark truth about the search for life. Not every world in the habitable zone offers a gentle welcome. Yet just 40 light-years away, an entire family of Earth-sized planets presents a far more compelling case. The star is TRAPPIST-1, a faint red dwarf so cool you could look directly at it without harm. And orbiting this star is a planetary system unlike any other we have found. 7 rocky worlds, all roughly the size of our own, are dancing in an incredibly tight formation. The entire system could fit comfortably within the orbit of Mercury around our Sun. This cosmic proximity means a year on some of these worlds is just a day and a half long. Within this celestial commune, one world stands out as a prime candidate for life, TRAPPIST-1e. It sits squarely in the middle of the star's habitable zone, the Goldilocks region where temperatures could allow for liquid water to pool on its surface. Its Earth-like size and rocky composition suggest a familiar landscape, perhaps of mountains, valleys, and most importantly, oceans. The presence of so many sister planets in the same system raises an astonishing possibility. If TRAPPIST-1e does host a liquid water ocean, its sky might offer a breathtaking view. Several of its sibling worlds would appear as large as our moon or even larger, hanging in the sky as constant, magnificent companions. But this compact arrangement comes with its own mysteries. The planets are so close that their gravitational pulls constantly tug on each other, likely heating their interiors through friction, much like kneading dough warms it. This tidal heating could power volcanic activity on the seafloor, creating hydrothermal vents. On Earth, such vents are thriving oases of life, entire ecosystems that exist completely independent of sunlight. Could the same be true in the deep, dark oceans of TRAPPIST-1e? The planet represents a new kind of hope, a world where the very forces that create extreme environments might also be the engines that spark and sustain life. The existence of a world like TRAPPIST-1e hints at a galaxy teeming with possibilities, but the first true confirmation that we were on the right path came from a different cosmic sentinel, a planet named Kepler 186f. This world, discovered in 2014, marked a profound turning point in human history. For the very first time, we knew with certainty that Earth-sized planets, worlds that could resemble our own, do indeed orbit within the habitable zones of other stars. Before this discovery, the possibility was just a theory, a hopeful whisper in the dark. Kepler 186f made it a fact. This distant world, about 500 light-years away, circles a red dwarf star much cooler and redder than our Sun. Its orbit within that golden region means that under the right conditions, liquid water could theoretically flow on its surface. The planet itself is only about 10% larger than Earth, making it one of the most similar worlds to our own we had found at the time. Yet its stellar environment is utterly alien. Imagine standing on the surface of Kepler 186f. The sunlight bathing the landscape would not be the familiar yellow-white of our Sun, but a deep, perpetual crimson. The star would appear much larger in its salmon-colored sky, a constant, dim ember. This different light could have a dramatic effect on any potential plant life. Photosynthesis would have to adapt to these redder wavelengths, possibly painting the landscape in shades of black or gray to absorb every possible photon. The planet also likely faces the same challenge of tidal locking, with one hemisphere in permanent day and the other in endless night. This could create ferocious winds as the atmosphere tries to equalize the extreme temperature differences between the two sides. So, while Kepler 186f proved that worlds of our size and potential exist, it also taught us that life, if it is there, would have to be as resilient and strange as its sun is red. It stands as a milestone, a silent declaration that our pale blue dot is not a singular miracle, but perhaps just one version of a common cosmic theme. Lurking in the cosmic shadows 40 light-years away is a different kind of hopeful world, a planet named LHS 1140b. This is not a fragile Earth twin, but a super-Earth, a colossal rocky world nearly 7 times more massive than our own. Its immense gravity would make every step feel like carrying another person on your back, and its composition is likely rich in iron, a dense metal that gives the planet a profound gravitational pull. This very density is a cornerstone of its promise, as it could be the key to holding onto a precious resource, a thick global atmosphere. While Proxima b might be stripped bare by stellar flares, LHS 1140b's powerful gravity could cling to a protective atmospheric blanket, one capable of retaining heat and distributing it around the planet. This is crucial because it orbits a red dwarf, and like its cousins, it is probably tidally locked. A substantial atmosphere could prevent the daylight side from scorching and the night side from freezing solid, instead creating a temperate band in the twilight region where conditions might be just right. But the most compelling feature of this system is the star itself. LHS 1140 is a remarkably quiet and stable red dwarf. It does not suffer from the violent tantrums of its stellar siblings, meaning it bathes its planet in a far gentler, more constant light. This rare tranquility gives any potential chemistry of life a stable environment in which to experiment and evolve over billions of years, free from the sterilizing blasts of radiation that plague other systems. Here, around this calm star, a massive world of rock and iron might just be cradling a secret beneath a warm, protective sky. But stability is a rare and precious commodity around a red dwarf star. A mere 11 light-years away, a world named Ross 128b offers exactly that, a gentler version of the red dwarf promise. This planet is a neighbor in cosmic terms, one of the closest potentially habitable worlds we have ever found. It is a rocky world with a mass very similar to Earth, and it too orbits within its star's habitable zone. But the star itself is the real story. While Proxima Centauri is a tempest, Ross 128 is a placid pool. It is one of the quietest red dwarf stars we know, a stellar body that rarely, if ever, erupts in the life-sterilizing flares that threaten so many other promising worlds. This profound calm means that Ross 128b has likely enjoyed billions of years of uninterrupted environmental stability. Its atmosphere, if it has one, has not been systematically shredded by stellar radiation. Its surface has not been periodically scorched by ultraviolet and X-ray bursts. On a cosmic timescale, this is a world that has been given the gift of time, a long, quiet afternoon in which the complex chemistry of life could potentially begin and evolve without constant interruption. Imagine a planet bathed in a perpetual, deep red twilight from its small, cool sun. A world where the forces of erosion and geology work slowly, undisturbed by celestial violence. The very tranquility of its star makes Ross 128b one of our most compelling targets in the search for a second genesis of life. Just 12 light-years away, a silent and ancient star holds a world that scores higher than any other on the scale of Earth-likeness. Teegardens Star B is not merely promising, it is, by the numbers, the most Earth-like exoplanet we have ever discovered. This rocky planet orbits an ultra-cool red dwarf, a star so faint and diminutive it emits most of its energy as infrared heat. Nestled firmly within the heart of its star's habitable zone, this world experiences stellar conditions that could allow for average surface temperatures remarkably similar to those found here on Earth. The possibility of liquid water flowing across its landscape is not a far-fetched dream but a plausible reality based on its orbital position. Yet the entire system is shrouded in profound mystery, primarily because of its age. Teegardens Star is ancient, a stellar relic that has likely been burning for 8 billion years or more. That is nearly twice the age of our own solar system. This means that Teegardens Star B has had an immense, almost unimaginable head start on the story of life. While Earth's biology was just beginning its first tentative experiments, this world could have already been a mature, living planet for billions of years. What kind of life could arise in such a different stellar environment? Its sun would be a deep, dark red orb in the sky, and the daylight, such as it is, would feel like a perpetual, warm twilight. Because the star is so calm and stable, the planet might even rotate, avoiding the harsh fate of tidal locking that plagues other red dwarf worlds. With ample time, stable conditions, and the potential for liquid water, Teegardens Star B stands as a haunting question. Has this ancient world been a solitary orb of stone and ice, or has it, in its incredible age, already written chapters of a biological story we can only begin to imagine? That profound age raises a question about maturity. Could some worlds be even better suited for life than our own? Over 1,000 light-years away, a planet named Kepler 442b presents a compelling argument. This world orbits a star fundamentally different from the tempestuous red dwarfs we have encountered, a stable and gentle K-type star, often called an orange dwarf. These stars are the Goldilocks of suns, not too big and volatile, not too small and dim. They offer a perfect balance of longevity and warmth, burning for tens of billions of years with a serene consistency that provides a stable stage for planetary evolution. Kepler 442b is a super-Earth about 1/3 larger than our planet, and it completes an orbit around its calm star every 112 days. The most remarkable fact, however, is the light it receives. Kepler 442b basks in a stellar flux almost identical to that of Earth. It gets just about the same amount of energy from its orange sun as we do from our yellow one. This key similarity means that, with a sufficiently thick atmosphere to trap and distribute that heat, its surface temperatures could be remarkably Earth-like. Some advanced climate models even suggest that under the right conditions, this world could be more habitable than Earth. Its larger size and stronger gravity could help it maintain a protective atmosphere for eons, and its stable, long-lived star provides a far more predictable and enduring environment than our own sun, which will one day grow too hot for life on Earth. So while we search for Earth twins, we may find that Earth's ideal form is a slightly larger world, bathed in the gentle, persistent glow of an orange sun, a planet that could potentially offer a more stable and longer-lasting home for life than the one we know. Sometimes the most profound discoveries are not made in distant star fields, but in data we already hold. Tucked away in old observations from the Kepler Space Telescope, scientists found a world that had been overlooked, a hidden gem named Kepler 1649c. When they reanalyzed the numbers, the result was breathtaking. Here was a planet almost exactly the size of our own Earth, a near-perfect twin in terms of its physical dimensions. Even more compelling, it orbits squarely within the habitable zone of its red dwarf star, a region where the stellar energy it receives is remarkably similar to what Earth gets from the Sun. Early estimates suggested its equilibrium temperature could be astonishingly close to our planet's own average. The realization sent a wave of excitement through the scientific community. Kepler 1649c was not a new observation from a powerful new telescope. It was a rediscovery, a potential paradise that had been hiding in plain sight within the vast digital archives of a completed mission. It was a powerful reminder that our cosmic census is still incomplete, and that other Earths might be waiting not in the unexplored darkness, but in the data we have already gathered, simply awaiting a fresh perspective. This world stands as a testament to patience and to the promise of second looks, a beacon that suggests our closest cosmic cousins might be closer than we think, quietly orbiting in the data all along. Our search for life often focuses on finding perfect Earth twins, but the galaxy seems to favor a different kind of world entirely. Just 12 light-years away, a star named GJ 1061 anchors a compact family of super-Earths, and one of them, GJ 1061c, presents a classic puzzle of planetary potential. This star is another quiet red dwarf, a stable and long-lived beacon, and around it orbit at least 3 rocky planets, all more massive than Earth. Planet C sits right on the inner edge of the star's habitable zone, a precarious and fascinating position. This is the frontier between a temperate world and a scorching hellscape. The energy it receives from its sun could lead it down one of 2 dramatically different paths. With a thin atmosphere, GJ 1061c might be a cool, rocky desert. But if it possesses a thick, dense blanket of air, the outcome hangs in the balance. That atmosphere could act as a perfect insulator, creating a global greenhouse effect that traps stellar heat and warms the surface to potentially comfortable Earth-like temperatures. This is the hopeful scenario where a world larger than our own cradles a stable climate. Yet there is a grave danger. If the greenhouse effect spirals out of control, the planet could undergo a catastrophic transformation, a runaway process that would bake its surface and boil away any oceans, turning it into a twin of Venus, a searing world shrouded in toxic clouds. GJ 1061c is a testament to a simple, profound truth. We are finding that compact systems of super-Earths around calm red dwarfs are not rare exceptions. They appear to be one of the most common planetary architectures in the Milky Way. The discovery of this world and its siblings tells us that the building blocks for life, rocky planets in stable orbits around long-lived stars, are scattered almost everywhere we look. The ultimate question is not whether such worlds exist, but what delicate balance of atmosphere and geology determines their final, life-giving fate. NASA TESS mission delivered a landmark discovery with TOI 700d. This world holds the distinction of being the first Earth-sized planet found by TESS orbiting squarely within its star's habitable zone. It is a rocky world, only about 20% larger than our own, circling a calm and quiet M-dwarf star. Like many planets orbiting such stars, it is almost certainly tidally locked, presenting a permanent day side and a permanent night side to its sun. Yet sophisticated climate models have painted a surprisingly hopeful picture of this world. They suggest that with a substantial atmosphere, TOI 700d could possess a global ocean. The models show how air currents could effectively circulate heat from the scorching day side across the entire planet, preventing the night side from freezing solid and potentially maintaining liquid water across its entire surface. The true significance of this world, however, lies with its star. TOI 700 is relatively bright and close by cosmic standards, making it a perfect laboratory. It is a prime target for the most powerful space telescope ever built, the James Webb Space Telescope. Webb's advanced instruments are designed to do something once thought impossible, to analyze the light filtering through a distant planet's atmosphere. By studying the starlight that passes through the air of TOI 700d, if it has any, astronomers could detect the chemical fingerprints of water vapor, methane, carbon dioxide, and even potential biosignatures, gases like oxygen that might be produced by living processes. This world is not just a dot of light anymore, it is a front-row seat, a promise that we may soon have our first real data on the air of another potentially living world. The detection of water vapor in the atmosphere of a world beyond our solar system was a landmark moment, and it happened around a planet named K2-18b. This super-Earth, orbiting a red dwarf star about 120 light-years away, sits squarely within its star's habitable zone. For the first time, we had direct evidence that a potentially temperate world possessed one of the most crucial ingredients for life. But what kind of world is it? K2-18b is a fascinating puzzle, a world caught between two identities. It is about 8 times the mass of Earth and more than twice its size. This places it in a mysterious category, right on the dividing line between a rocky super-Earth with a thick, extended atmosphere and a mini-Neptune, a planet with a small, rocky core enveloped by a vast, deep global ocean beneath a crushing hydrogen-rich sky. The water vapor detection suggests an atmosphere rich with humidity, but the planet's true nature remains hidden. If it is a rocky world, its surface could be a water world, a global ocean with no land in sight, shrouded by a steamy, cloud-filled atmosphere. If it is a mini-Neptune, the pressures deep in its gaseous envelope would be so immense that liquid water could not exist in a familiar form, potentially creating exotic states of matter. This ambiguity makes K2-18b one of the most important worlds we have ever found. It is a laboratory for understanding the diversity of planets that can form in the habitable zone, proving that the cosmic recipe for a living world might come in forms far stranger than we ever anticipated. Hidden in the data from just 31 light-years away, another super-Earth emerges from the darkness. GJ357d is a world nearly 6 times more massive than our own, a substantial rocky giant orbiting within the habitable zone of its quiet M-dwarf star. Its discovery was made using the transit method, where a planet passes in front of its star from our point of view, causing a telltale, repeating dip in the star's light. This method is a gift to astronomers because when a planet transits, the starlight filters through its atmosphere, imprinting the light with the chemical signatures of the gases present. GJ357d is close enough and its star is bright enough that it presents a perfect opportunity for this kind of atmospheric investigation with the James Webb Space Telescope. But what would those observations reveal? The planet's significant mass suggests 2 very different possibilities. It could be a terrestrial world, a vast continent of rock and iron with a gravity much stronger than Earth. Or its size and position hint at another fascinating scenario. It might be a water world, a globe completely shrouded by a single, deep, planet-wide ocean, with no land masses breaking its watery surface. Imagine a world with no mountains, no shores, just endless ocean under a hazy sky, its depths holding secrets under pressures we can scarcely comprehend. The future observations of this nearby giant could tell us which path nature chose, revealing whether we are looking at a colossal Earth or an aquatic abyss waiting to be explored. This search for habitable worlds often leads us to the dim, red lights of dwarf stars, but what about suns that mirror our own? Over 40 light-years away, a star named HD 40307 offers a different kind of promise. Orbiting this sun-like star is a super-Earth known as HD 40307G, a world that stands out precisely because of its stellar parent. While countless habitable zone planets huddle close to cool red dwarfs, this planet basks in the light of a star much more familiar to us. Its orbit within the habitable zone is far more distant and leisurely than those of its red dwarf cousins. A single year on this world lasts about 200 Earth days, a rhythm that feels far less alien than the day-long years of the TRAPPIST-1 system. This greater distance from its star makes the phenomenon of tidal locking highly unlikely. Instead of one side forever facing the light and the other trapped in darkness, HD 40307G could have a regular rotation, creating a familiar cycle of day and night. Imagine the profound difference this would make. A sunrise and sunset would grace its horizons, its surface would experience a more even distribution of heat, and its weather patterns could be far more temperate and stable. But this very similarity to our own solar environment is what makes such worlds so difficult for us to find. Bright, sun-like stars dazzle our telescopes, and the gentle dip in light caused by an Earth-sized planet transiting is incredibly faint and easily lost in the stellar glare. Discovering HD 40307G was a triumph of precision, a reminder that while red dwarfs may offer the easiest targets, the true Earth analogues, those orbiting stars like our own, are still waiting silently in the light, challenging us to find them. Far out in the constellation Lyra, a world almost the same size as our own circles a star much older and cooler than the Sun. Kepler 62f is a testament to the resilience of life's potential, a planet that challenges our definition of a habitable world. It orbits a K-type star, an orange dwarf, but it sits far out in the colder, outer reaches of that star's habitable zone. At this distance, the stellar energy it receives is faint, like a distant ember in the sky. Without a helping hand, this world would be a frozen ball of ice, a snowball planet locked in a permanent deep freeze. Yet this very distance opens the door to a fascinating possibility. The key lies in the planet's atmosphere. If Kepler 62f has managed to hold onto a thick blanket of air, rich in greenhouse gases like carbon dioxide or methane, something remarkable could happen. That atmospheric blanket could trap just enough of the star's weak heat to raise global temperatures above freezing. The result could be a planet-wide ocean, a single, globe-spanning sea of liquid water hidden beneath a hazy, insulating sky. This scenario transforms our search. We are no longer looking just for planets in the perfect spot, but for worlds that can create their own warmth, that can use their atmosphere as a cocoon against the cold of space. Kepler 62f expands the frontier, teaching us that a world on the outer edge, a place we might have once dismissed as too cold, could be one of the most common abodes for life in the cosmos, a silent water world waiting in the faint light of an aging sun. Kepler 452b earns its nickname as Earth's cousin for a very compelling reason. It orbits a star almost a perfect twin of our own Sun, a stable G-type star burning with the same familiar yellow light. This world is only about 50% larger than Earth, placing it firmly in the category of a super-Earth, and it completes a leisurely orbit of 385 days, a year strikingly similar to our own. For over 6 billion years, this planet has been basking in the habitable zone of its sun-like star, a span of time even longer than Earth's own history. That immense period of stability is what makes this world so profoundly tantalizing. It has had more than enough time for the intricate chemistry of life to begin, evolve, and potentially flourish. The planet's size strongly suggests it is a rocky world, much like our own, and a world of that scale likely has active geology with volcanic activity and plate tectonics. On Earth, this geological churning is essential for recycling carbon and regulating our climate over eons, creating a stable environment for life. Imagine standing on the surface of Kepler 452b. The sun in the sky would look almost identical to our own. The landscape might feel hauntingly familiar, and the sheer length of its stable past raises an almost overwhelming question. If life emerged here, what has it become with that incredible head start? This world is not a fleeting hope around a tempestuous dwarf star, but a mature planet in a mature system, a mirror held up to our own world that shows us one possible and deeply resonant path a living Earth might take among the stars. Just 12 light years from Earth, a planetary system is locked in an intricate gravitational dance, and at its heart is the super-Earth Wolf 1061c. This massive rocky world, over 4 times heavier than our own, presents a stark paradox of potential and peril. It orbits squarely on the inner edge of its star's habitable zone, a precarious position between a temperate climate and a runaway greenhouse effect. The energy it receives from its dim red sun could theoretically allow for liquid water, but any miscalculation in its atmospheric composition would push it over the edge into a Venus-like inferno. The planet's climate is not governed by its star alone, however. Wolf 1061c is not a solitary world. It shares its tight orbital space with at least 2 other planets, a smaller inner sibling and a larger outer one. These neighbors exert a constant rhythmic pull, subtly altering the planet's orbit over thousands of years. This gravitational nudging, a phenomenon known as orbital forcing, could trigger dramatic climatic shifts. Imagine a world where the gentle tug of neighboring worlds acts like a cosmic thermostat, periodically tilting the planet's axis or stretching its orbit. These changes could plunge the planet into ice ages or pull it closer to its star, baking its surface in cycles that repeat over millennia. The stability needed for life to gain a foothold is constantly challenged by these celestial rhythms. Wolf 1061c is a lesson in cosmic context, a world whose fate is written not just by its own atmosphere, but by the persistent rhythmic gravity of its family. A mere 12 light-years away, a star almost identical to our Sun shines in the constellation Cetus. Tau Ceti has been a fixture in science fiction for generations, a beacon for imagined interstellar voyages, and the reality is just as compelling. Orbiting this familiar star is a colossal world, Tau Ceti e, a super-Earth with a mass at least 4 times that of our own planet. This giant resides in what astronomers call the optimistic habitable zone, a region where the stellar energy it receives could, under the right conditions, permit liquid water to exist. Yet this world sits on a razor's edge between 2 terrifyingly different fates. Its orbit is remarkably close to its star, a year there lasting just 168 Earth days. This proximity bathes the planet in intense light and heat, pushing it toward a critical threshold. One path leads to a potentially habitable, if extreme, environment, a world of deep oceans and a thick, protective atmosphere. The other path leads to a scorching hellscape, a super-Venus. In this scenario, the planet's proximity would have triggered a runaway greenhouse effect long ago, boiling away any oceans and shrouding the world in a permanent, crushing blanket of toxic clouds. The fundamental question is one of geology and atmosphere. Did Tau Ceti form with enough water to become an ocean world, or was it born dry and infernal from the start? The answer lies hidden beneath the glare of its sun-like star. Adding to the mystery is a tantalizing yet unconfirmed discovery surrounding the entire Tau Ceti system. Observations suggest it may be surrounded by a massive disk of debris, a sprawling field of asteroids and comets far denser than our own solar system's Kuiper belt. This presents another paradox. Such a rich reservoir of icy bodies could be a delivery service, constantly bombarding the planets with water and the organic compounds essential for life. Alternatively, a constant rain of impacts could pose an existential threat, regularly sterilizing the surface of any world in the system and preventing life from ever gaining a foothold. Is Tau Ceti a water-rich super-Earth awaiting discovery, or is it a stark warning of how easily a world in the habitable zone can become a permanent furnace? This nearby giant holds the secret to one of the most fundamental divides in planetary science. The cosmic neighborhood grows even stranger just 22 light-years away, where a planet named GJ667cc orbits in a system with not one, not two, but three suns. This super-Earth, a world nearly 4 times the mass of our own, circles a dim red dwarf star that is itself locked in a gravitational embrace with 2 other stellar companions. Despite this celestial complexity, the planet resides squarely in its primary star's habitable zone, and the amount of stellar energy it soaks up is almost identical to the light Earth receives from our solitary sun. This creates a fascinating paradox, a world with a familiar energy budget orbiting within a profoundly alien family portrait. The 2 other stars in this triple system would appear as incredibly bright points of light in J667c's sky, shining with the intensity of a full moon or even brighter. Their gravitational influence, however, is likely too distant to severely disrupt the planet's stable orbit around its host star. This stability is the planet's greatest gift, allowing it to maintain a consistent climate over billions of years, a crucial requirement for any potential biochemistry to take root. Yet the very nature of its red dwarf sun presents the same old challenge, a high probability of tidal locking. One side of this super-Earth would be a permanent landscape of scorching daylight, while the other is an eternal frozen plain. The thin ribbon of twilight between them, the terminator line, could be the only region where temperatures are truly moderate. Could a thick atmosphere redistribute this heat, creating a world more welcoming than its initial conditions suggest? GJ667cc stands as a testament to nature's versatility, proving that the potential for life is not confined to simple, single-star systems, but can arise even within the complex and beautiful dance of multiple suns. The first confirmed world of its kind, Kepler-22b, marked a pivotal moment in our cosmic quest. Discovered in 2011, it was the very first planet found by the Kepler telescope to orbit squarely within the habitable zone of a star similar to our own Sun. This was not just another data point, it was a profound validation of the mission itself, proving that the tools and techniques we had developed could actually find these distant, life-giving oases. But what kind of world did we find? Kepler-22b is a celestial puzzle, a world whose true nature remains beautifully elusive. It is about 2.4 times the radius of Earth, placing it squarely in a category for which we have no local example. It is larger than our rocky home, yet smaller than the ice giant Neptune. This ambiguous size means it could be one of 2 utterly different kinds of planets. It might be a super-Earth, a massive rocky world with a thick atmosphere and perhaps even a global ocean, a single planet-wide sea. Alternatively, it could be a mini Neptune, a world with a small, solid core enveloped by a deep, gaseous hydrogen and helium atmosphere. A place where the very concept of a surface vanishes into crushing pressure and exotic ices. This fundamental uncertainty is what makes Kepler-22b so iconic. It represents a fork in the road of planetary evolution, a reminder that the habitable zone is not reserved solely for Earth twins. It can host worlds of bewildering diversity, from water-drenched globes to gassy enigmas. Its discovery expanded our imagination, forcing us to ask not just if a world could hold life, but what form that world might even take. HD 85512b pushes the very definition of a habitable world to its absolute limit. This super-Earth, discovered orbiting an orange K-type star, does not sit comfortably in the middle of the life-giving zone, but clings precariously to its inner edge. The energy it receives from its sun is intense, nearly as much as the scorching planet Venus gets from our own sun. On a barren rock, this would be a death sentence, creating surface temperatures hot enough to melt lead. Yet this world presents a fascinating possibility, one where its own atmosphere could be its salvation. The key lies in something we see every day here on Earth: clouds. Advanced climate models suggest that if HD 85512b has a substantial atmosphere with just the right amount of cloud cover, those very clouds could act as a planetary sunshade. They would reflect a significant portion of the intense stellar radiation back into space before it could heat the surface to unbearable levels. For this delicate balance to hold, the clouds would likely need to be composed of water vapor, and they would need to cover at least 50% of the planet's sky. This creates a breathtaking image, a world where constant, brilliant white clouds are not just weather, but the very shield that keeps the planet cool enough for liquid water to potentially exist in pockets or across its surface. Finding this world was a triumph of a different kind of detection. Unlike the Kepler telescope that watched for planetary shadows, astronomers discovered HD 85512b using the radial velocity method. They did not see the planet pass in front of its star. Instead, they detected the subtle wobble of the star itself. The planet's gravity, as it orbits, tugs its star back and forth, causing the star's light to shift very slightly in color. By measuring this tiny, rhythmic dance in the starlight over years of observation, scientists could calculate the planet's mass and orbit. This technique revealed a world at least 3.5 times heavier than Earth, orbiting its calm orange sun once every 58 days. HD 85512b stands as a lesson in atmospheric alchemy, a world that should be a furnace but might just be a temperate haven, all depending on the simple, life-giving presence of a blanket of clouds. Kepler 443b is a world that tests the very limits of our definitions. Orbiting a star over 2,500 light-years away, this planet exists in the cold, dim outskirts of its star's habitable zone. Its position is so distant that it receives barely a third of the stellar energy that Earth enjoys from the Sun. At first glance, its location within that golden region suggests potential, a place where liquid water might theoretically pool. But the planet's physical nature tells a different, more sobering story. Kepler 443b is a giant with a radius more than twice that of Earth. This immense size places it squarely in a category that is likely incompatible with a rocky, Earth-like surface. The overwhelming probability is that this world is not a super-Earth but a mini-Neptune. Imagine a planet with a small, solid core of rock and ice, but one that is utterly drowned by a deep, global ocean of hydrogen and helium gas, an atmosphere so thick and crushing that it transitions seamlessly into an exotic, superheated fluid. There is no familiar shoreline, no solid ground, just an endless, deepening abyss where pressures become so immense they defy comprehension. The discovery of Kepler 443b serves as a crucial reminder of a fine line we are only beginning to perceive. Our telescopes can tell us a planet's size and its orbit, but they cannot always see its soul. A world can be in the perfect place, but if it is a gaseous enigma rather than a terrestrial haven, its potential for life as we know it vanishes. This planet highlights a fundamental challenge in our search, forcing us to ask for every new discovery we make, are we looking at a water world or a gas-shrouded giant? Gliese 832c is a world of dramatic possibility, a super-Earth that once stood at the very pinnacle of our search. Orbiting a quiet red dwarf just 16 light-years away, this planet is over 5 times more massive than our own, a substantial rocky giant. For years, it boasted one of the highest Earth Similarity Index scores ever recorded, a numerical promise that it could be the closest thing to an Earth twin we had ever found. Its orbit is short and snug, a mere 36-day year spent within the habitable zone of its calm star, but this very orbit is the source of its greatest mystery. Unlike many tidally locked worlds, Gliese 832c follows a slightly elliptical path, a stretched-out circle around its sun. This simple orbital shape has profound consequences. As the planet travels, its distance from the star changes. It swings closer, bathing in intense warmth, then arcs farther away, cooling in the more distant chill. This rhythmic dance could create powerful seasonal shifts across the globe. Imagine a world where the entire climate pulses with the rhythm of its year, where summers are sweltering and winters are deep and intense, all compressed into a cycle of just a few Earth weeks. The planet's substantial mass and gravity could be the key to stabilizing this wild ride, holding onto a thick atmosphere capable of distributing this heat and moderating the extremes. Before missions like TESS unveiled dozens of new candidates, Gliese 832c was a beacon, a prime example of the kind of large, stable world we hope to find around every quiet red dwarf. It remains a classic puzzle, a reminder that a planet's potential is written not just in its position, but in the precise geometry of its path around its sun. The cosmic census often reveals entire families of worlds, and sometimes it is the second child that holds the greatest promise. Far beyond our solar system, the star Kepler 283 is orbited by a pair of planets, and the outer world, Kepler 283c, presents a compelling portrait of a temperate super-Earth. This planet, about 170% the size of our own, orbits a stable K-type star, an orange sun that offers a serene and enduring light. Its orbit places it squarely within the star's habitable zone, a region where the energy it receives is just right for the possibility of liquid water. Its size strongly suggests a rocky composition, a terrestrial world of stone and metal, not a gaseous mini-Neptune. But the true value of Kepler 283c is not found in isolation, it is illuminated by its sibling. The inner planet, Kepler 283b, orbits far too close to the star, a scorched world where any water would have boiled away eons ago. By studying both planets together, scientists can engage in comparative planetology. They can ask why one world became a potential oasis and the other a furnace, even though they were born from the same cloud of dust and gas around the same star. The differences in their atmospheres, their densities, and their histories become a controlled experiment on a cosmic scale. This comparative approach is transforming our search, allowing us to move beyond studying individual points of light and toward understanding the life stories of entire planetary systems. Lytton Star B feels almost within reach. Just over 12 light-years away, this super-Earth circles one of our nearest stellar neighbors, a quiet red dwarf with a profound stillness that makes it an ideal cosmic laboratory. The planet itself is a substantial world, over 2.5 times the mass of our own, and it orbits squarely within its star's temperate habitable zone. But like so many worlds around such stars, it likely faces a single, stark reality: tidal locking. One hemisphere is permanently sunlit, a landscape of endless day, while the other is a frozen wilderness of eternal night. The thin ribbon of land between these two extremes, the terminator line, could be a world of its own, a place of perpetual sunrise and sunset where temperatures might be just right for liquid water to exist. What makes Lytton Star B so extraordinary, however, is not just its potential for habitability, but its accessibility. The entire system is moving directly toward our solar system. In tens of thousands of years, it will be even closer, a near neighbor in the cosmic dark. This trajectory, combined with its relative proximity and quiet star, places it at the very top of the list for one of astronomy's most ambitious future projects, direct imaging. Imagine a telescope, perhaps a vast array of instruments in space, not just inferring a planet's existence from a wobble or a shadow, but physically blocking out the blinding light of its star to capture a single, pale pixel of reflected light. That tiny dot would be Lytton Star B. From that single point of light, we could analyze its spectrum, determine the composition of its atmosphere, and even map the rudimentary features of its cloud cover. We would not see continents or oceans, but we could learn if it possesses the chemical signatures of a living world. This nearby super-Earth is more than a candidate, it is a future portrait, a promise that one day we might look upon the first photograph of a world that could be home. A longer orbit can rewrite the entire story of a world. Kepler 1544b is an Earth-sized planet with a year that unfolds over 168 days, a rhythm far more leisurely than the frantic orbits of many red dwarf worlds. This places its annual cycle in a fascinating category, similar to that of Mars in our own solar system. Such a prolonged journey around its star has profound implications for its climate and its potential to nurture life. The primary gift of a longer orbit is stability. A planet that moves more slowly experiences less extreme variations in the stellar energy it receives throughout its year. This consistent energy budget allows for a more temperate and predictable climate, one that could persist for billions of years without the wild swings that might regularly freeze or scorch a world's surface. This stability is the bedrock upon which complex life could potentially build. But this longer year also introduces the possibility of deep, pronounced seasons. Imagine a world where summer is not a matter of a few months, but a drawn-out, gradual warming that lasts for dozens of Earth days. Winters would be equally long and profound. The axial tilt of Kepler 1544b would be the master of these seasons, just as it is on Earth. A significant tilt could create dramatic shifts in temperature and daylight between its hemispheres, driving powerful weather patterns and ocean currents that circulate nutrients across the globe. For any potential life, these long, reliable seasons could provide a stable, repeating cycle for growth, migration, and adaptation. This world is a reminder that the potential for life is not just about a planet's position, but also about the pace of its journey, a slow and steady orbit that offers the precious gift of time. The boundary between a living world and a gassy enigma is often blurred. Among the thousands of discoveries from the Kepler telescope, a world named Kepler 1638b stands as a perfect example of this cosmic ambiguity. This planet occupies a frustrating and fascinating category known as a sub-Neptune. It is larger than our own rocky Earth, but smaller than the ice giant Neptune in our solar system, placing it in a size range for which we have no local example. Its orbit is undeniably promising, carrying it through the habitable zone of its sun-like star. The energy it receives could, in theory, permit liquid water. But the fundamental question remains, what exactly is Kepler 1638b? Is it a massive, water-rich super-Earth with a solid surface, or is it a mini-Neptune, a world with a small, dense core utterly swaddled in a vast, deep atmosphere of hydrogen and helium? This is the central challenge with sub-Neptunes. A planet of this size could have formed in two dramatically different ways. If it coalesced from drier, rocky material closer to its star, it might be a terrestrial giant. But if it formed farther out, in the colder regions of the protoplanetary disk where ices were abundant, it could have greedily gathered a tremendous envelope of light gases, becoming a world without a true surface. Imagine an ocean not of water but of gas, an atmosphere so thick and heavy that it transitions seamlessly into a supercritical fluid under the immense pressure. There would be no shore to stand on, no ground beneath your feet, just an endless, deepening haze where the very idea of a landscape vanishes. For life as we understand it, this distinction is everything. A rocky surface offers stability, geology, and the potential for chemistry to play out in pools and soils. A gaseous shroud offers no such foothold. Kepler 1638b is a silent lesson in planetary diversity, a reminder that a planet in the perfect orbital position can still be utterly alien, its true nature hidden beneath a veil of mystery and gas. Further out in that same celestial family, TRAPPIST-1G presents a colder, more glacial version of its sibling's promise. While Planet E sits in the comfortable middle of the habitable zone, Planet G orbits on its chilly outer frontier. The energy it receives from its faint red sun is far weaker, suggesting a world with a much lower equilibrium temperature. On a barren rock, this would mean a permanent global ice age. Yet this very distance opens the door to a different kind of hopeful world, one that might mirror the icy moons of our own outer solar system. The surface of TRAPPIST-1G could be a frozen crust of water ice, hard and glittering under the dim red light. But beneath that frozen shell, something remarkable could be hiding. The planet's substantial size and its location within the system create a powerful internal heat source. It is constantly flexed and squeezed by the gravitational pull of its 6 sibling planets. This tidal heating, the same force that keeps the subsurface ocean of Jupiter's moon Europa liquid, could be warming the interior of TRAPPIST-1G, maintaining a vast, dark, global ocean between its rocky core and its icy ceiling. Imagine a world with no surface lakes or rivers, but a hidden sea larger than all of Earth's oceans combined, trapped beneath a crust of ice miles thick. In that eternal darkness, warmed by the planet's own geological heart and shielded from the hazards of space, the chemistry of life could have been brewing for billions of years. This potential is magnified by the system's most beautiful feature, its orbital resonance. All 7 planets are locked in a precise gravitational dance. For every 2 orbits Planet G completes, Planet F makes 3, and Planet E makes 4. This rhythmic harmony keeps their orbits stable and predictable, but it also means their gravitational tugs are constant and rhythmic. This perpetual, gentle kneading is what generates the internal heat that could power a subsurface ocean. TRAPPIST-1G is a testament to the idea that a living world does not need a sun-drenched surface. Life could flourish in the absolute dark, in the warm waters under the ice, in an abyss lit only by the faint, steady warmth of a planet's own core. Yet even a world of profound calm can be shattered by celestial violence. Kepler 1652b is a rocky planet almost exactly the same size as our own, a near-perfect Earth twin in physical dimensions. It orbits a red dwarf star squarely within the habitable zone, a world that from a distance appears to have all the right ingredients, but its star is a cosmic tempest, a place of frequent and furious eruptions. Imagine the surface of this Earth-sized world suddenly bathed in an ultraviolet glare far brighter than its dim sun, as a stellar flare unleashes a wave of radiation powerful enough to damage DNA and strip away the air. This is not a rare event for Kepler 1652b. It is a regular and brutal fact of life. The very flares that threaten to sterilize the planet also make it a classic example, a template for the most common type of habitable zone world we have found. Red dwarfs make up the vast majority of stars in our galaxy, and most of them are volatile in their youth. This means that for every quiet oasis like Ross 128b, there are countless more like Kepler 1652b, worlds caught between the promise of liquid water and the peril of a fiery star. The story of life on such a world would be one of resilience, of finding refuge deep underground or beneath a protective ocean, waiting out the stellar storms. This planet represents the stark reality of our cosmic search, reminding us that a perfect orbit and a familiar size are only part of the equation for a living world. The starlight from a nearby sun holds the secret to our greatest question. Just 137 light-years away, a star named K23 shines with a brightness that makes it a perfect cosmic laboratory, and orbiting this star is a world called K23d. This is a super-Earth, a planet about 1.5 times the size of our own, and it makes its home squarely within the star's habitable zone. But what makes this world truly special is the path it takes. K23d is a transiting planet, meaning it passes directly between its star and our telescopes here on Earth. Each time it transits, a tiny fraction of the star's light filters through the planet's atmosphere, and within that faint, altered starlight are the chemical fingerprints of the gases swirling in that alien air. Because the star is so relatively bright, that signal is clearer and stronger than for many other distant worlds. This puts K23d on the short list of prime targets for the most powerful space telescope ever built, the James Webb Space Telescope. Webb's instruments are designed to catch that filtered starlight and break it down into a spectrum, a barcode of colors that reveal the atmosphere's composition. Scientists will be searching for the subtle signs of water vapor, of methane, of carbon dioxide. But the ultimate prize, the signature that would change everything, is the simultaneous presence of oxygen and methane. Here on Earth, these two gases react with each other and disappear quickly unless something, most likely life, is constantly replenishing them. Finding them together in the air of K23d would be the most compelling evidence we have ever had for biology beyond our solar system. It would suggest a world not just of chemistry but of constant living activity. Yet the opposite result, an atmosphere devoid of these tantalizing hints, would be just as profound. It would tell us that a planet can be the right size and in the perfect spot and still be a sterile rock. K23d is more than a point of light, it is a test. With every orbit, it offers us a chance to read the first line of a story that may or may not include life. GJ 1214b brings our journey to a close not with a familiar Earth, but with a world of pure, unadulterated mystery. This super-Earth, orbiting a red dwarf star just 48 light-years away, is one of the most thoroughly studied exoplanets of its kind. For years, astronomers have trained their most powerful instruments on it, analyzing the starlight that filters through its atmosphere during its frequent transits. The results have been both definitive and deeply puzzling. The planet's atmosphere shows no chemical fingerprints at all. It is a flat, featureless blanket, absorbing light uniformly across all colors. This strange uniformity is the key to its secret. The only thing that can create such a perfect blanketing haze is a thick, dense atmosphere, likely rich with water vapor or high clouds composed of salts or other exotic compounds. This points to two possible realities, both of which are utterly alien to our experience. GJ 1214b could be a steamy, high-pressure water world. Imagine a global ocean not just covering the surface but extending hundreds of miles deep with no land in sight. Under the immense pressure and heat, the water at great depths would not be a familiar liquid but a strange, supercritical fluid, a state of matter that is neither liquid nor gas. Alternatively, the planet might be a mini Neptune, a world with a small, rocky core utterly engulfed by a deep, hydrogen-rich atmosphere so thick and hazy that it completely obscures whatever lies beneath. In either scenario, the idea of a solid, walkable surface vanishes. This world, sitting in its star's habitable zone, serves as our final, crucial reminder. The term habitable zone describes a region of temperature potential, not a guarantee of a living landscape. A planet can be in the perfect spot and still be a global, pressurized ocean or a shrouded gas ball, environments where the chemistry of life as we know it would struggle to find a foothold. GJ 1214b is the boundary of our imagination, a world that challenges our very definition of what it means to be a planet that could support life. The true test for these 30 worlds is about to begin. We have mapped their orbits and estimated their size, but the next great leap is to search for the faint chemical whispers of life itself in their atmospheres. Astronomers call these clues biosignatures, gases that, if found together, strongly suggest the presence of biological activity. The most promising of these is oxygen. On Earth, our abundant oxygen is a direct product of life, constantly replenished by plants and photosynthetic bacteria. Without life, oxygen would quickly vanish, reacting with rocks and gases and disappearing from the air. Another powerful biosignature is methane. While geological processes can produce small amounts of methane, vast quantities, especially when found alongside oxygen, point toward biology, as these two gases naturally destroy each other unless something is actively producing both. Beyond these natural signs, we also listen for technosignatures, the detectable traces of an advanced civilization, such as narrowband radio transmissions or the unique chemical signatures of artificial industrial gases. The hunt for these signs relies on a revolutionary technique called transmission spectroscopy. When a distant planet transits passing in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere. The atmosphere acts like a chemical filter, absorbing specific colors of light depending on what gases are present. By analyzing this filtered starlight with incredibly sensitive instruments, we can read the atmosphere's unique barcode, identifying the fingerprints of water vapor, carbon dioxide, methane, and yes, even oxygen. This is where our newest eyes on the cosmos come in. The James Webb Space Telescope, with its massive gold-coated mirror, is already pioneering this work, peering into the atmospheres of planets like K23d and LHS 1140b. Its infrared vision is perfect for detecting the heat signatures of molecules in the air of these distant worlds. Soon, it will be joined by a new generation of ground-based giants, like the extremely large telescope being built in Chile. With a mirror nearly the size of a blue whale, this colossal instrument will directly image nearby exoplanets, blocking out the blinding glare of their stars to capture their faint, reflected light for the first time. Together, these observatories will transform our list of candidates into a catalogue of living worlds. They will tell us which of these 30 orbs are not just in the right place, but are truly breathing, their atmospheres pulsing with the chemistry of a living biosphere. This collection of worlds is a testament to cosmic creativity. We have found planets bathed in eternal crimson light, globes shrouded in impenetrable haze, and frozen shells hiding deep, dark oceans. Some orbit in serene solitude, while others dance in complex families of 3 sons or 7 siblings. The sheer variety is staggering, from super-Earths with crushing gravity to Earth-sized gems buffeted by stellar flares. This incredible diversity tells us one thing with absolute clarity. The universe is not just making copies of our solar system, it is experimenting. It is building an endless gallery of planetary possibilities. The existence of 30 such worlds in our immediate cosmic neighborhood, a tiny fraction of the sky we have searched, suggests something profound. If so many different kinds of planets can fall within our broad definition of potentially habitable, then the total number across the Milky Way must be astronomical. Life, if it exists, is likely not a singular, fragile miracle confined to planets that look exactly like our own. It could be a tenacious force, thriving in the deep oceans of a tidally locked world, clinging to existence in the twilight band of a super-Earth, or flourishing under the gentle glow of an ancient orange sun. The potential for life appears to be woven into the very fabric of the galaxy. So the next time you find yourself under a clear night sky, look up. Remember that you are not just looking at points of light, but at suns, and around those suns, entire worlds are spinning. Some may be deserts, some may be water worlds, and some, just maybe, are looking back. The greatest discovery in human history is still waiting, and it begins with a single, simple act of curiosity. Keep wondering, keep looking up, and join us next time as we continue our journey into the cosmos.